Should we start? Okay, should we start? Is that okay? Well, thank you very much for coming to today's seminar. I think online we are okay. Try to keep the microphones muted in case. Is that okay? No, it comes from you. Does it come from you? No. Okay. So we have two presentations today from Dr. Catherine Homer, who is a senior research fellow here. And the title of the presentation is Early Learning from Remission, an evaluation of the NHS low-calorie diet program. The second presentation is from our student, Daniel Hay, a PhD student, yes. And the title is Ice Hockey Helmets During Collision Head Impacts, Testing and Helmet Design. So we're very glad that we have Daniel here. It's the first presentation from a student that we have, and we hope that he can build on this and we can have a conversation on his research. And we also hope that all the papers all the presentations will proceed to become peer review articles. I mean, that's the ambition of the seminars. So we can provide, the SPARC team can provide some practical help if this is required in this direction. So without further ado, I leave Catherine to do the presentation and then we'll proceed with Daniel. Okay.
Yeah. Okay, hopefully everybody's got that on the online. So thanks for asking me to present today. I'm Catherine Homer. As Tim said, I'm a research fellow, senior research fellow in physical activity, wellness and public health, and one of the co-leads for the Healthy and Active 100 theme at the AWRC. So I'm going to talk today about a study I'm involved with that's an NIHR funded study. And it's an evaluation of the national NHS low-calorie diet programme. So I'll just talk you through what that is first before I go into the actual research. So the low-calorie diet programme has been commissioned by NHS England as a kind of a bid, if you like, to help improve diabetes, reduce reliance on diabetes medication, and achieve remission for people on the programme. It came out of the NHS long-term plan in 2019, and it was piloted with support of NHS England, Public Health England, and Diabetes UK. An overview of the programme. It's pretty complicated, so apologies for this quite messy flow diagram. And I guess the point of this being that we're evaluating a real world complicated programme, complex intervention, and we're evaluating it across various different areas. So in the first instance, back in 2021, I think, it was commissioned in 10 areas, and they were ICS, so integrated care system areas across South Yorkshire and Basset Law, and the other ones that you can see on there. So it started off being piloted, and we were asked to evaluate that pilot programme. Last year, early this year, it was rolled out to a further 10 areas. So we've taken 10 more geographical areas on board. And we're just going, the NHS England is just going into a national procurement process, so it will be rolled out nationwide from next year. So all our findings that we're producing now are feeding into that procurement process. So it is having some kind of real world policy impact, which is great. In terms of what it is, it's for anybody between 18 to 65 years old. They've had a diagnosis of type 2 diabetes within the last 6 years. They've got a BMI, so a body mass index. That's the way that we measure our our weight relative to our height, for over 27 kilograms per metre squared, or 25 in people of Black, Asian or minority ethnic groups. And there are other criteria within there. So if you're pregnant, if you've got uncontrolled diabetes, there's other things going on behind that, but that's essentially it. Basically, it's a primary care referral into the system. They're referred on to one of 4 initial providers that deliver their service in those 11 areas, and then they have 12 weeks of TDR, which is total diet replacement. So essentially that's where we have no food for 12 weeks and you have 800 calories a day made up of 4 soups or shakes. So it's stripping out meals completely. For some providers, they offer supplement bars within that, but essentially calories a day. Somebody's looking at it, I think.
Anil, can you mute yourself? Mute your phone.
And then after 12 weeks, people are supported to reintroduce food back into their diet, and that's a stepped program. So in week 1, they might drop one of the soups and bring in a meal. Week 2, and then it builds up, so you're back on 4 regular meals a day. And then at weeks 19 to 52, the people are supported to kind of support this healthy period of weight loss or weight loss maintenance, and then they're supported to kind of go out and be more physically active and consume a healthier diet. There are different behaviour change support delivery models for that. There's a group-based intervention, which is all online. There's one-to-one, and then there's digital support, which is done through an app where people are signposted to community peer support groups or are signposted to resources on their app. So we're kind of trying to evaluate across 21 areas, across 4 different providers and 3 different delivery models with real-world people. Hence why I say it's a little bit messy, but it's great. So what we're wanting to do is deliver a co-produced comprehensive qualitative and economic evaluation. There's some other NHS quant data that's taken place through alongside it, so we're feeding into that, and it's about kind of looking at the long-term cost effectiveness, but looking at whether it's implementable across and equitable across different groups. And if you want more information about the methods and things, there's a protocol that I've linked to on there. Just to give you a bit of a kind of idea of the goings on and who's delivering it. So I'm the project manager of the qual piece of work on it, and there are various different programs of research that are going on under that, but we've got kind of a massive group of people behind us, from researchers, health economists, qual researchers. We've got a big PPI group within that, absolutely instrumental to the workings of the group. We've got 2 PhD students, and then we've got specialist advisors from various different clinical and non-clinical roles that are in England and beyond. We've got some colleagues in America supporting us. So the project, how do we do this? We've got 5 work streams within it, and there are very different kind of parts to those work streams. Work package 2 and 3 are the main ones for me, and that's where we're doing some session observations. So we're sitting in sessions and observing what's going on over the 52 weeks. We're doing some longitudinal patient interviews. So we're speaking to people at their 12 weeks, 18 weeks and 52 weeks to see how they're going on. We're using some photo voice techniques within that. We're doing focus groups with the providers of the service. So they're the four companies that are providing the service across the different areas. And we're interviewing healthcare professionals. And we're also offering the opportunity for all people that take part in the programme to complete a survey. So there's lots of different data going on. There's a documentary review of all service spec data and contextual information from the areas. And then there's kind of this package around transferability. So how does all that data that we collect, how can we transfer our findings into practice to inform this recommissioning of the programmes? So far, this is just kind of a summary of where we're at. Surveys have been not greatly completed, despite lots and lots of speaking to the providers. But we are working with providers to kind of increase that. We've done interviews with people that lead the programme in each locality, and we've done that at the end of year 1 and the end of year 2 to see what's changed in the implementation of the programme and the marketing, the communications, the training, and all the stuff that goes on between kind of getting an intervention commissioned and actually rolling it out in the area. So we've spoken to people that are responsible for that. We've done all the provider focus groups. We're doing the digital observations and in-person observations. So I've sat in on one of the providers groups for the whole course of the programme and kind of observed what we've gone, and we've linked that up to a behaviour change taxonomy to see whether they're meeting the behaviour change goals within that. We've done the referral staff interviews, and we're currently underway with the longitudinal interviews, and that's my bit really, and it's fascinating just having that amazing opportunity to kind of understand how people are faring through the programme and what's working or not for them. I'm just going to stop recording now because this is data that I'm not sharing. We're not sharing wider at the minute. So if you just bear with me a sec. Amazing, thank you. Yeah. There we go. Last point over these next few slides, PPI, and anyone that knows me know that I talk about PPI and how important it is for patient and public involvement. For anybody that doesn't know, it's about getting people with lived experience or getting the general public to kind of comment on our research. This PPI team, and they're amazing, they're from all over England. They've all got lived experience of type 2 diabetes or obesity, all different backgrounds. They started working with Louisa, the PI, Professor Louisa Ells, right at the beginning of this kind of the idea for this project, and they've informed every single stage of the piece of work. They're brilliant, such a great team. And working. So kind of their role, they've co-developed the funding application, they've co-developed the study protocol, all the patient-facing materials. We've had hours of meetings where they've gone through every single interview, every schedule, every participant information sheet, every bit of advertising, every email, and they've commented on that. That really helps when we're going through to ethics. We've had talks about, you know, what is it, is withdrawal the right word? Is it withdrawal? Is it do you not attend? These really things that we don't necessarily think about on a daily basis. These guys have helped to strip it down and really helped us, and that helps us get engagement within the project, undoubtedly. For some of the PPI, they've joined us on interviews, and that's been great because say there's been me and one of the team interviewing. So that individual that we're interviewing all feels comfortable then, because there's someone with lived experience. They know how they're feeling, they know what they're going through, they're sat and they're asking questions, and their level of compassion and understanding and empathy is just, it adds so much more to the interview. They've co-presented at different meetings and conferences, and we bring them in to do that all quite regularly, and they've co-authored some of the publications. We've got one out in the Perspectives in Public Health Journal that was actually written by the team about their involvement in this piece of work. They've co-developed the study website for some films to kind of help with recruitment, and every journal article, we've committed that every journal article we write from this, we will get a lay PPI summary on the website at the side of every journal article. Because when we're talking about behaviour change techniques and taxonomies and cost effectiveness and all that really, really complicated stuff, actually we'll get one of the guys to come in and do their summary. So it's just a bit more acceptable and understandable, if you like, to other people that we're trying to target with this piece of work. It's not just about us learning as well, it's about NHS England, and it's about people with lived experience learning. And just a kind of a few quotes on there about what it means. Oh gosh, you guys can't see that. Sorry, I should have done that before. About what it means to people to be involved in this. And these guys will go on and they're getting involved in kind of a follow-up study that we're planning. Yeah, they're fab, and they get a lot out of it as well. So anyone that's doing any work, I'd recommend kind of getting a group like this on board within, because I don't think we'd have got this bid without these guys. So in terms of next steps, we've got the project finishes next November, which feels very, very quick now. So continue with data collection, continue with the data analysis. We have a SWAP study. I can't remember the full acronym, but it's about the impacts of the low-calorie diet on osteoarthritis. So somebody's taking bloods, and we're looking at kind of physiological changes as well as some longitudinal work around that. It's disseminate. We're getting to that stage, and we're informing the national NHS England procurement process, which is great, because then hopefully they take on board some of what we're saying, then it will have impact in the next round. And we're looking at NIHR, so National Institute for Health Research, Health Services, and DR, yes, HSDR, fault there, money to extend data collection. And we'd ideally like to speak to some of those people. We've interviewed 12 months, we'd like to speak to them 3 and 5 years, because we're very aware that there's this weight cycling, and it's how they kind of manage these long-term gains that they might have seen throughout these 12 months. And that's me. Sorry if that went on.
Brilliant. Any questions?
for a great presentation. Really interesting work. Given all of the things you talked about, where did that original program come from? Where was it designed? It seems to be some very large flaws that you've highlighted throughout.
Yeah.
How did that come about and how did it get rolled out?
Just let me.
Okay.
So you got the
The recording I resumed, yeah, so we should be all right. Right. So, hi everyone. We made it through technical difficulties. I'm Daniel. I'm a PhD student at the Sports Engineering Research Group since 2019, and I'm looking at concussions and helmets in ice hockey. I'm currently in my final year and mainly writing up at this stage, so I'm able to give you quite a nice summary of what I've been up to the last 3 years, or what we've been up to. John and Leon are sitting in the back. They were part of the whole journey. So the background and motivation for my research: ice hockey is a fast-paced and physical sport, and despite rule changes and helmet developments, head injuries and especially concussions are still very common. If we look at the common reasons leading to concussions in the table on the bottom left, we can see that 7% are caused by falls, where the head impacts the ice or the surrounding boards, so very, very stiff, rigid surfaces. 88% are caused by contact with opponent players, and 5% by contact with teammates on the ice. So usually something like a shoulder or an elbow. So either way, much softer or more compliant impacting bodies than the ice. And from experience, I can tell you that there can be quite a bit of contact in hockey. I even found a picture of myself in Harlem colors, crunching a junior student at last.
Dan, Dan. So, sorry to interrupt, Dan. I can't see any slides. I don't know if you're sharing them.
Oh, okay, hold on. I'll try to fix that.
Sorry.
I thought I did.
It's me.
My bad, sorry.
Sorry.
Is that better?
Amazing, thank you.
All right, thank you. Sorry about that. All right, yeah. Here we were. Yeah, quite a lot of contact. And we can say that 93% of concussions in ice hockey come from a contact with another player on the ice. So the graph on the right here shows a typical linear acceleration versus time curves for fall type head impacts and collision type head impacts in ice hockey. And we can see that these collisions, which is the gray line, result in lower peak accelerations, but increased impact durations compared to the falls. And we do know that these scenarios have a high risk of concussions. So current certification standards test ice hockey helmets with a linear guided drop test method. A helmeted head form is dropped onto a perpendicularly aligned anvil fitted with a rigid polymer surface. The linear acceleration is measured in the head form, and if that linear acceleration does not exceed a threshold of 275 Gs, the helmet is deemed suitable. So that setup represents a fall to the ice and played a big role in reducing the amount of severe head injuries. But as we just heard, that's only 7% of concussions, and 93% of concussions in ice hockey have a much more compliant impacting body, and the standards right now don't account for these events at all. Helmet evaluations in published research describe a whole range of different test protocols and different test methods. So all these pictures are from different labs all over the world. All of those try to evaluate ice hockey helmets. And admittedly, most of them provide some kind of benefit in making better estimates for concussion or head injury probability. But there is little to non-consensus out there, which is the preferable method, really. And even then, or even if there were, it's still a lot of expensive lab equipment required, which isn't really available to many researchers. So that limits the work that can be carried out in the field quite a lot. So from this, we had two main interests in my PhD project over the last 3 years. So one is a majority of concussions come from collisions where current helmets aren't really effective. And number two is that the test method in test standards isn't really thorough enough, while in published research, there is little agreement on how to do it, and it requires quite a lot of lab equipment that most people don't have. So the first part of my PhD project was developing a test method to replicate common head impacts in ice hockey, including to be able to match what's been described as a collision type head impact or a concussive collision type head impact. So we used a simple free fall drop test method because we want to reduce complexity and require lab equipment as much as possible. And we dropped the instrumented head form from a height of 1 meter, resulting in 4.5 meters per second impact velocity, measured linear and angular acceleration in 6 degrees of freedom, and that throughout 30 different impact scenarios and a total of 540 impacts. We then matched all impacts with a reference data set for concussive collisions. So the red crosses on here, I hope you can see them all right, represent the reference data set. And we calculated the normalized pairwise distance from these reference values, which is the gray shaded area. And then we added our own data set to be able to see which of our impact scenarios has the closest match to concussive collisions, and found the best match for when we applied a 48 millimeter layer of EVA foam on a 45-degree oblique anvil, which is the blue markers in those two graphs. So we now have a test method to obtain good results to estimate a helmet's performance in a collision head impact in ice hockey, which looks like that. So compared to the earlier slide that was purposefully a bit messy, I think this is a very simple and very easily reproducible test method. And we were also already able to adapt this test method into other sports headwear and carried out some exciting consultancy work that I've been told is confidential and I'm not allowed to talk about. But yeah, we used it in other sports already as well. I'll move on here for time reasons. But if you're interested in this, thanks to the SPARC Catalyst funding we received, we have quite a representative data set there, and we're able to publish in 2 conference papers. And the journal article is under review since April, so hopefully coming out before Christmas. So if you're interested in this test method, please get in touch or check out the papers. So for the second part, we remember that helmets are only effective during falls, but most concussions come from collision type head impacts. So let's start by looking at how helmets are designed and how they work or don't work. So helmets in all applications really consists of a minimum of 2 layers, where one is a stiff outer shell to spread the load over a maximum area, and 2 is a soft liner that compresses, which is traditionally foam, because foam is cheap, light, and effective. But unfortunately, it's always only effective in the loading condition it's designed for, and it's always only one loading condition as well. So the diagram to the right you can see here shows compressive stress versus compressive strain of cellular structures. It is a bit simplified because it doesn't consider temperature or strain rate, but it's good enough to get the point across I'm trying to make. So the area under each curve is the energy absorbed per unit volume. And we want to maximize that area before the cellular structure densifies and we see that sharp rise in the curve. So for this middle line with the shaded area below, that is basically what we would want. And that's sort of what it would look like for a fall type head impact with an ice hockey helmet. So the area under that curve is maximized before the foam bottoms out and we get that sharp increase. If the material is too soft in the helmet, we get that very low curve here. So we still get an area under the curve, but it's not the maximum, it's not ideal before the helmet bottoms out and we don't really get any protection anymore from it. And if the helmet liner is too stiff, which is the top 2 curves really, and the case during ice hockey helmets and a collision impact, there's not much compression going on at all. and therefore not much energy is absorbed before it actually goes to the head and brain. This is a very basic helmet with actually, well, 3 layers because it's 2 densities of foam, but it's a very basic setup. Modern helmets try all sorts of new technologies. So the cyclists in here might be familiar with MIPS or have heard of wave cell. That's all, or both attempts to at least the wave cell should help with that a little bit as well. And things like B3O, so shear thickening polymers, have also become increasingly popular recently, in case anyone has heard of that. But we think we have our own potential solution for the problem. So we are looking at an adaptive mechanical metamaterial with what we think has the potential to improve helmets during collision head impacts without compromising performance during falls. So it consists of 2 hyperelastic materials making up what we call a bibeam, and 2 of those bibeams making up 1 unit cell of the metamaterial. So 1/2 of the beams, in this example on the slide here, blue, is highly strain rate dependent, so visco-hyperelastic. And the other side, the red one, is mainly strain rate independent. And at low compression rates, the strain rate independent material is stiffer. So if we now compress them in axial direction, so a bit like this, something really interesting happens because of the aspect ratio of the beams, they will always start to buckle, and they will always buckle towards the stiffer side. So if we now increase the compression rate, so just squish them faster effectively, at some point there's a threshold point that we exceed where the strain rate dependent material becomes the stiffer material and the beam starts buckling in the opposite direction. So if we tailor this threshold of buckling, a change in buckling direction between the loading rates of a fall type head impact and a collision type head impact, we could achieve a very stiff system during falls or fall type head impacts where we need exactly that, but a rather compliant system during collisions where current helmets aren't effective because they are too stiff at the moment. We're working on creating a helmet liner from this design that can basically switch between 2 states. So basically as shown here, in red, the buckling inwards or against each other, a very stiff material or system, and in black, where they buckle outwards, a rather compliant system or layer. But before we could do anything, we needed to be able to control and understand the fabrication process of the materials we wanted to use. And we also required the material parameters for the design process and the FEA simulations we are running right now, actually. So we got 4 different 3D printable thermoplastic polyurethanes and did a series of material characterization tests with them, which namely were tensile tests at 4 strain rates, along with a digital image correlation, compression tests at 6 different strain rates, and stress relaxation tests at 2 different strains. So we got ourselves all the material parameters we need to numerically simulate the materials. Again, if you're interested in this kind of stuff, it's all published and it's open access along with a data repository for all 4 TPUs. So if that's something that interests you, get in touch or read the paper. With that data collected, we start modeling and fabricating our bibeams. They are at like this size right now, so they're rather small, but because it's a geometric phenomenon we're looking at, it's scalable to any size virtually. And then we stuck them in our Instron test machine out at the AWRC. And in the videos here, it's important to bear in mind that the stiffer side is always the lighter side, and the softer side is always the darker half of each bibeam. And then depending on the orientation and the gap between them, we got 3 different loading scenarios, where one is buckling outwards, where they just buckle unrestricted. 2 is a pushing through scenario, where they have an initial contact, but because it's not exactly the same in the real world ever on both sides, one beam pushes the other away, and we then end up with unrestricted buckling again. And 3 is buckling inwards, where the gap is too big for them to push each other away, and they start pressing against each other. Also important here is none of the materials has a massive strain rate dependent effect. This is a proof of principle with materials that we know how they will behave. But adding the force versus displacement measurements to the left, we have the unrestricted buckling and a really nice baseline curve thanks to that. In the middle, we have the pushing through, where we have that initial contact with a peak, but then as soon as the buckling is unrestricted, we sort of get to that baseline level. When free, the buckling inwards, we don't have that drop, at least not at strains lower than 0.2. And the peak forces measured for the same displacement are almost 3 times higher, which is quite a lot considering it's the exact same beams, just placed in opposite orientations this time. So what we want is to switch between what just has been the left and now the blue outward buckling, and the right, now orange, inward buckling, to depending on the impact event. So we get those 2 very different states of helmet or liner deformation. And a similar thing can be achieved with shear thickening polymers, but that's a more progressive change, whereas this is a very abrupt change at this very threshold that is tailorable. And from what we've done so far, we can say that the metamaterial works in the intended way in 1 unit cell. And the FEA simulations we ran confirm that as well, or suggest that as well. So we now use the numerical model, the FEA, to scale it up with more than 1 unit cell to actually create a sheet layer of the metamaterial. And with different configurations and designs, we're trying to find the most promising design approach that we then want to pursue and produce a final prototype effectively. Whatever that might look like eventually, if I can manage to stick around for a little longer after PhD with a postdoc or something similar, we would like to actually produce a helmet liner from it and replace the conventional foam layer of a helmet with it, and then put it through our own test protocol, as well as like some other helmet testing protocols, to hopefully see that helmet performance is much greater during collisions, but just as good as current helmets during falls. That is the vision, that's the idea behind it. So with both the test method that opened up the field to many more researchers with an interest in head impacts, and the material design, if we can get it to work, we hope to reduce the number of sustained concussions a lot. And this could make ice hockey, but also other sports and basically any helmeted activity much safer in the future. That brings me to the end. Thank you very much. If you have any questions, please feel free to ask or get in touch. Thank you. Do I keep this up? Do I stop sharing? Do I... No. Okay. Yep. Yes, please.
How much does it weigh compared to the previous size?
Compared to the foam?
Yeah.
There's quite a lot of gap in it in the end, because we need to leave like a certain gap in between. And these are just example materials, so we could go stiffer or softer either way. So it's really up to how many of these we will stick into a layer. But because there will be quite a bit of cavities, we don't expect it to be much heavier than the current foam.
So if I understand well, the idea is that you combine these in different directions so that the design can accommodate both soft blows and yes.
Yes. So basically, we will always need 2 of these, and then either buckles away from each other or towards each other and stops each other. But if we then add up more of these, and in the real world, we'll never have those perfect loading conditions that the Instron produces for us. So we will unit cells in different orientations, which is what the FEA is doing for us as we speak, basically, hopefully. The simulation doesn't break again. Yeah, so that, and we might even be able, but we haven't looked at that yet, so it's just a bit of a hope right now, that because we have 2 stiff layers then with these beam structures in between, that we can also do a bit about like angular acceleration, which is a big topic in helmets right now. But we haven't looked at it yet, so it's hard to actually make a statement. But we're hoping. Yeah.
Thank you for a great presentation.
Thank you.
A really good review of your I was wondering what your thoughts are on other sports which have this kind of multiple condition impact. You know, ice hockey is a really great example.
Yeah.
In your research, what have you found in terms of other sports where this might be applicable?
As you rightly said, ice hockey is the perfect example for it. And we haven't expanded it too far out yet, but even something like American football, the majority comes, as everyone who has a bit of an interest in the sport, comes from them running into each other. But there's also the turf, and they play from everything between -10 to +40 degrees probably. So effectively, if they play in the winter, the ground is frozen, so they have the same range of head impacts. If we take out the projectile, which is the puck in ice hockey, which does hardly cause any concussions ever, by the way.
Other questions around, you said 93% concussion be caused by impact with the player. Does the severity of concussion vary similarly? And is what specifically is that measured? Was it reported?
No, like flat out, no. Concussion measurement and diagnosis is always a bit of a limitation in any study that you'll find. Because in sports like ice hockey or American football, where a bit of a warrior mentality is pushed, most players will actually try to hide, even though they know full well they have a concussion, they will try to hide it from the medical stuff and coaching stuff so they can keep playing. There's quite a bit of literature out there to suggest that. And from personal experience, yeah, we do that. So it's hard to tell. Yeah.
Do you do anything with playing with the amount of heat these are exposed to test how that changes the voting issues? I'm thinking like you have an ice hockey player who's working really hard, their head is going to warm, right? So is that
you're definitely right. So the helmet liner will usually get close to the head's temperature during competition. The only thing that would change that is something like American football. They take off their helmets quite often when they're, let's say, their O-liners and the D-lines out. A lot of them take their helmets off, then they will cool off. But in ice hockey, we tend to keep them on. And yes, temperature plays a big role. We haven't looked at that yet, but if it should ever become a system that goes in helmets, the standards test between 0 and 40 degrees Celsius. So it will be an important thing to look at because temperature dependence is a thing. Anything?
So there is an optimum temperature under which the cellular.
Pardon me?
There is an optimum temperature for the efficiency.
Probably there is. Like an absolute ideal temperature would be there, but the important thing is to not get too much of a variance introduced by temperature. So we will have to stay in a range where the helmet is doing his job. So, but there should be plenty of materials out there to make that happen. But unfortunately, as I keep being reminded, I'm not a product designer, I'm a researcher. So right now I'm trying to do a proof of principle and find evidence that it works rather than building a helmet that I'm then trying to sell in the shops. Maybe soon.
So that would be for your PhD?
What I just presented is all part of my PhD, yeah, that I'm in the process of writing up, which sometimes goes really well, sometimes it's very slow.
Any other questions?
Thank you very much.
Yeah. Okay, thank you very much for coming. The next seminar will be the last before Christmas, and that will be on the 13th of December, 1:45, also in the room D104 in this building, and will be from Nick Putieski, who will address the effects of posture on cerebral blood velocity during the acute phase of stroke, and by Dr. Alice Boulas, who will address 3D anthropometry and Isaac. So that will be the anthropometry and the standards of measuring it. Isaac, I think, is the international association, International Society for the Advancement of Anthropometry. So I hope that will be extremely interesting. And since it's the last seminar, I hope you will all come back.